Okay, so let me go back to speaker view and let's go to questions. Okay, so I will unmute you and let me see. I have questions about, so who would like to go first? I have a ton of questions in chat, but I also have a ton of comments there as well. I guess, so David Mathis was asking about inertia control of the Rindler horizon. David, do you want to ask that directly, sir?
I don't even remember where it's at. First off, Mike presented a lot of information.
I know, he went through a lot.
Short amount of time. And just trying to take notes on his lecture was a little bit interesting. So Mike, are you suggesting that you can provide eventually inertia control of the Rindler horizon or some other event horizon?
Yes, I can control, I think we can control inertia using synthetic Rindler horizons.
And how do you expect to construct such a thing? Is it going to be, does it require a metamaterial to do so? Or is it, yes, is it an electromagnetic phenomena only?
It's an electromagnetic phenomenon only. So I'm assuming that Unruh waves are composed, as is known, of all the fields, but at the moment I can only see that we can affect the electromagnetic component of it using metal plates, metamaterials, that sort of thing.
Okay. Thank you.
Okay, thank you, David. You know what? Let me go to Jeremy Reese and see if we have any YouTube comments. Jeremy, do you have anything from YouTube?
Let me just unmute real quick. Sorry about that. We had, first off, Mike, I'd like to thank you so much for joining us today. That was fantastic. I've read a lot of your work. I've dived into a lot of these concepts, so it was a little easier for me than, say, someone who's taking notes and all new to this stuff. For me, it was like a roadmap of all these little bits and pieces of a lot of stuff that I had read or knew about, but you did a brilliant job of connecting it just now in this presentation. This was fantastic.
Thanks.
I wanted to ask a little bit more about how schemes for where we're, of course, an engineering conference, and I want to ask a little bit more about the M drives, which I think that dates back to, like, what, 2007?
Maybe 2001.
2001. Wow, that far back. So the M drive, and also what you know about engineering projects and groups that are working on this, and anyone else that you might know of, that, because I'm always interested in getting new speakers to present. So anyone that you could recommend, name drop away.
Yeah, there's Martin Theimer in Germany, who I mentioned in my talk, who's been looking at M drives, and I think has a null result, a zero thrust at the moment. There's somebody at I think he's at the Naval Research Lab, called Mike McDonald, who's looked at them as well. And I think he also got a zero result.
Yeah, and I believe Roger Scheuer will actually be joining us on April 3rd, if I remember correctly. He'll be presenting on the M drive. And so we could ask him more about that and how that interacts with the quantized inertia model when he joins us too.
And also, my second part question was, have you ever heard of Todd Desiato? You mentioned Hal Puthoff in some of the VSL stuff. I know Todd has published extensively on VSL GR, and I was wondering if you had ever read some of his work.
No, I haven't read any of his papers, I'm afraid. I have heard of him. I know the name. I'll make a note of it.
Yeah, definitely.
Okay, well, Jeremy, thank you. Thank you. So let me mute you back out. Let me go to, let me see. Hector Serrano is asking about espresso. That doesn't count, Hector. And let me see. Jonathan had a question, and I should apologize. I'm trying to scroll through chats. There's a lot of them in here. Jonathan was asking about spacecraft design. Jonathan?
Yeah, so thank you for the talk, Mike. I've got a question about how the energy generation and propulsion applications of quantized inertia would fit together in a single spacecraft. Now, as you've mentioned on social media before, you could do an M-drive style free energy device by spinning a pair of thrusters around an axis to generate current. And then eventually that hits over unity if you do it in the right way. So would the artificial horizon set up from doing that with, say, the axis of rotation along the axis of a spacecraft interfere with a horizon that you're trying to set up for a thruster on the aft end?
The horizons would be independent.
Okay.
So that would be okay. That wouldn't be the most efficient way to do it. The most efficient way to do it would be move the cavities to a nanoscale. So then you wouldn't need any input power at all.
Sure, I'm just thinking because like nanoscale materials are not exactly easy to make. And so something that you could build out of things like regular electronic components and steel and things like that would probably be a little more attainable. Like we've seen down in Boca Chica, cheaper construction makes up for a lot.
Yeah, okay, sure. Yeah, a lot of people become concerned about that because it looks like I'm getting energy from nothing. But my answer to that is that I published a paper recently showing that there's something called Landauer's principle, which states that if you erase a computer memory, what happens is that you reduce entropy in the system. So you have to produce energy, heat energy, to force entropy to go up again. And this is well known in the computer industry. It's Landauer's principle. So in quantized inertia, what happens is that a horizon forms and it cuts off part of space. So you lose information about space from your point of view. And I've managed to calculate that the energy released looks just like the energy you need for quantized inertia. So the energy is coming from information. So it's not anything, nothing. It's
okay, and thank you, Jonathan.
thanks.
Yeah, let me go to. I'm sorry, I'm jumping around again. We've got a lot. Michael Boyd, sir, can I ask you to go next?
Hello?
Wonderful, sir. Go ahead.
Okay. Hi, Mike. I'm curious to try and understand what relationship is between quantized inertia and vacuum energy. Is it directly or indirectly related?
So the way I think about the Honor effect is it's an excited vacuum. So it's an enhancement of the normal 0-point field. An accelerating object sees a more intense 0-point field than the one that we normally do.
Okay. So would you be knowledgeable about semiconductor physics?
No. No, I did a physics degree, but
do you know like in the photoelectric effect where you have
oh yes, yeah.
So basically you have a valence band and electron and what's called a conduction band electron. And the energy delta between the two is called the band gap.
Yeah.
And, okay, so my question is along those lines, do you think that that the vacuum energy has a band gap, like semiconductor, for example?
No, I'd say it doesn't. I wouldn't say it with 100% certainty, but I don't see any reason for the vacuum to have a band gap.
I've asked Hal Puthoff this same question, and he said no, doesn't think it has a band gap.
I think it'd be quantized, but no band gap.
So, well, for example, matter any kind of matter has a band gap. So like a silicon crystal has a 1.1 EV band gap. And then like a piece of carbon, like a diamond, has a 5.5 EV band gap. So in a gas, like hydrogen gas has a band gap too. And so that's why that kind of gives you the context of why I'm asking about. So there's basically nothing there in the vacuum to create the energy. Would you agree with that?
Well, yeah, there's no band gap. It's a very simple system as far as I've assumed so far. I don't think I can prove it to you, except that the theory assumes that there is no band gap, and it seems to predict a lot of things. So
yeah. Well, Michael, thank you. Let me move along again to Morgan Lynch, and I should apologize. They're starting to pile up on me, so I want to move through them. Morgan, are you there, sir?
Yeah, I'm here. Can you guys hear me?
Yeah, wonderful, sir.
Yeah, hi. Hi, Mike. This is my first time actually seeing you speak. I've been following your work. Actually, I think it's really interesting. I would say that I had a very nice discussion with Ulf Linhart at the Royal Society about a year and a half ago, and he had been proposing that there's this cosmological constant which comes from like basically a Hubble scale Casimir effect. And so I really like this idea that you're doing with this Unruh effect. I think it's actually really interesting. What I wanted to ask or maybe recommend. So you are proposing that you can produce a thruster based off of this essentially asymmetric Casimir effect based off of a Hubble scale and a Ringler horizon. And what I wanted to propose to you actually, which might be a fun idea, is to look for an analog gravity model of what you're describing. You know, what we all want to look at is advanced propulsion, right? And you might be able to actually find an analog system where you can realize what you're proposing. You know, I don't know if it's Bose-Einstein condensate or water or some sort of nanophotonic system, but there may actually be. Do you understand? You know, these guys in Nottingham and all of this stuff. I think you might be able to find a system to realize these things. I think it's a really cool idea.
Yeah, Ulf Leonhardt. I love his work. So he was at St Andrews, I think, before, but now.
Oh, nice. Okay, cool. Yeah. So I think this is really cool. I think but like in terms of like a proof of principle, I think you actually might be able to really kind of like hit one home with these things. So it's I'm looking forward to see what you guys are doing in the future. But I support what you're doing.
Okay,
it's really cool idea.
Yeah, analogs.
Well, wonderful. Well, thank you, Morgan. Thank you. Let me go to Hector Serrano, who is brewing espresso, but actually has a question. So go for it, sir.
Okay. Hi, Mike. I just got a very simple question. Who's the project manager at DARPA?
Oh, it was Mike Fiddy.
Who's his replacement?
Rohit Chandrasekhar.
Oh, wow. Okay. Now I know. Okay. That's all I asked.
Okay.
Thank you.
Oh, okay. Thank you, Hector. Let me see. Oh, Jeremy, would you like to go again, sir?
I would. Thank you. So I have a question, and it was about isn't the Schwinger limit the band gap of the vacuum in a sense?
I'm afraid you'll have to explain the Schwinger limit.
So the Schwinger limit's like we were talking about that band gap, and the band gap being the Schwinger limit would be that's like the limit where, say, if you have a high energy gamma, that it would the limit where the energies would produce particle and antiparticle production. It's that limit where you actually you can have coupling of matter and energy in the vacuum.
Oh, I see. So that's really huge, isn't it?
It is, I believe. This kind of relates to what I believe our last speaker was talking about with the solitons and the production of what he was referring to as solitons. And I had mentioned about we talked to you share some of these links on Twitter about the polaritons and stuff. University of Rochester is doing some interesting work with producing negative mass and negative energies and stuff in the laboratory with polariton and polariton condensates and stuff like that. I'm wondering if this might be like what's going on inside, these skin coatings and stuff. I don't know. This is what I've been researching lately in any case, but I don't know. Do you have any comment on that?
No, not at the moment.
No, not at the moment. Some stuff to look up though.
Okay.
Yeah, I'll look it up.
Okay, Jeremy, let me mute you back out. Sorry, I'm jumping around a little bit. Oscar, and I'm not sure what your question is, but would you like to go, sir?
Yeah, well, I wrote it in the chat. Hi, Mike. How are you?
Yeah.
Long time no see, but yeah, I'm really pleased to see that the project is advancing and the California connection is working well. I have a question. I mean, I fully agree with you. I really love your QI theory about galaxies rotation and the radiation. We spoke about this probably 1 year, a year and a half ago, but I still don't see how a metal plate can dump the inertia. And as you said, the plant won't be smashed on one side of the vehicle if the vehicle is a metal shape that blocks all the radiation from outside, because that contradicts a little bit the experience that we all have, that even in a submarine or even in a space capsule, you are subject to inertia.
Yes, but I'm saying that inertia is due to a gradient in the quantum vacuum. In the acceleration's case, an energized quantum vacuum. So a gradient will apply to every object within the spaceship and the spaceship equally. So it applies to every single atom in the volume equally. So there'll be no difference between the motion of all the objects. So the plant will not be smashed.
Yeah, but why we are not seeing that in our experience? Is because it's macroscopic, or because the thickness of the walls are not thick enough?
Oh, because well, normally what happens is that if you accelerate in one direction, a horizon appears in the opposite direction, which pulls you back. And if you accelerate at a very fast rate, the horizon is pretty close. Sorry, my camera's frozen up. It always does this after 1 hour. Maybe I should answer this question, then log back in. But yes, if you accelerate rapidly, your horizon is close and there's a huge acceleration on you from the horizon, pulling you back. But if you're able to control the horizons yourself, you can stop that from happening. You can put horizons wherever you want.
So that means that at low acceleration, we could see that effect, but at normal accelerations, we are not seeing it.
You should see it at all accelerations equally, but I'm saying that you can add synthetic horizons to offset it.
Yeah. Now, Mike, would you like to log back out and log back in?
Yes. Yeah. Okay. Sorry about that. Happens to my camera every hour.
No worries at all. Go for it, sir.
I'll see you soon.
Okay, and everyone, I hope I'm doing okay with the questions. Let me see. So let me see. So I guess we have Eric next, and then Michael Himes. Do you have a question, sir? I notice you keep unmuting yourself.
Yes, it's about the M drive.
Okay. If you can give him just a second till he's back on.
I kept losing my train of thought. I meant to ask him another question, and then I forgot what it was by the end of it, and I'm like, I'm rambling now. All right. No, but I remember what it is now. I wanted to ask him about his new paper on VS. So,
Okay.
variables
Well, yeah.
from the
So let me get, we have Eric and then we have Michael Himes. I want to get those two gentlemen, if that's okay, Jeremy.
No, I'll wait in line. I'm not rushing to the front or anything. Just popping in to fill the time while we're all sitting here, on downtime, dead air.
Yeah, no worries at all. No worries at all. I'm really excited. I think we have some really exciting guests and some big ideas too this week,
Yeah, I believe that Mike, well, it's a kind of topic because this is about propulsion, but QI has also implication for low energy nuclear reaction. In a paper, I think that there is a paper that Mike wrote about that, the hydrogen's atoms get enough force to smash together in small cavities, and that could explain why some crystal lattices can create nuclear fusion of hydrogen inside the
lattice fusion.
Yeah, low energy. Yes, low energy is cold fusion.
Yeah. No, it's interesting. Yeah, you mentioned that, and that's been picking up over the last year. I've been hearing more about. I think they're calling it lattice fusion these days, right? They change the name every year. They gotta stay one step ahead of the debunkers. So
yeah, it's because cold fusion had some implications that everyone wants to avoid. So that's why they're trying to find alternative names for that.
Yeah. Okay, and we're still waiting for Michael.
I think that Mike should get a new computer, new mic, microphone.
Yeah, I think. Yeah, well, and again, I should apologize to everyone for interrupting earlier. I thought the hum might be that it was too close to his fan, but maybe something else was going on. So. Yeah, and we can give him a few more minutes, and if he isn't able to log back in, that's also fine. I know, I'm just glad that he was able to give us. Well, he gave us a lot of his time. We also did a good Q&A session for him as well. We do have a few more, and then we have Jeremiah also. And let me see. So we do have Jeremiah. I have a question from Ziggy. I have a question from Eric. Question from Michael Himes. We'll probably do Michael first, and then Eric, and then Ziggy. So.
As you know, the M drive went to China.
No, I didn't know that.
Yes, and the Chinese built a whole UFO system based upon the M drive physics. Now, Mike was right about band gap. Copper, as a metamaterial, has a band gap, and the valence electrons, when accelerated in a scalar field, shed photons. It dumps mass. And all of this surrounds that. Most people don't consider things like crop circles, where you have the alpha wave ring current coming from the resonant cavity of the Earth. It's an Aether effect, but it's stirred by the scalar resonance spin in the of the transmitter. So you got this little vehicle hovering over the crops, and it's transmitting down to the ground. It penetrates the ground, and it stirs the alpha wave ring currents, which returns. And it's huge. It's like a huge dump of current.
Okay. Well, Michael, let me apologize. Mike just came back in. I have to find him. There we go. So, Michael, would you like to ask your question to Mike McCullough now?
I don't know whether he is aware of the link, the LC circuit of a transmitter in a scalar resonance with the ground, or the mirror image that the scalar resonance produces. So I would like to know if he can link those two things together.
Okay, and Mike,
I'm not sure I understand the question. The LC circuit.
oh yeah, he was asking about, Michael, you were asking about the M drive, right?
Right. It creates an LC circuit with the ground. It's a resonant circuit.
Oh, you're suggesting another reason for the thrust?
Yes. Are you familiar with the alpha wave ring current discharge? Look at a crop circle and see what happens under the little vehicle that makes those suckers. That's an alpha wave response.
Okay,
It's
I've heard
coming
of
right up
propulsion
from.
wave.
Okay, and is that something, Michael, could you spell that alpha wave? It's
ALFVEN wave ring current.
Thank you, sir. Thank you.
Totally overlooked by physics. Everybody's focusing on a vehicle. It's not just the vehicle. It's what happens around it.
Alvin wave ring current. Okay.
Right.
Yeah, that's something I think we'll all have to end up doing some research on to understand where you're coming from.
It's
okay.
so intense. It's so intense. The radiation is ionizing. There is a Z pinch in the return. It is huge.
Oh, actually, it looks like Jonathan Lane knows about it too. Alvenic wave ring current. Okay, well, so let me go to Eric Hermanson next. So Michael, thank you. Let me go to Eric.
Hi, Michael. How you doing?
Hi, yes.
Hi. Could you put up the slide with the Becker bot experiment?
Yes.
With the 100 Newton response?
Yeah, hang on.
You know, and I should mention for the Q&A session, especially because we ended a little early, just let us know. You know, we don't have to go a full hour, or we can go. We're flexible on time, Mike. So whatever your schedule looks like.
Okay, I'm okay at the moment. It's getting on towards midnight here, though.
Oh, you're in the UK?
Yes, I'm in the UK.
Oh, you're in Plymouth in the UK. I thought you were in Plymouth, Massachusetts.
It's 11:10 now. Yeah, so is that the one you wanted to see?
Yes. So so obviously this one experiment was the results were much different. They were about 1,000 times better than a lot of the other experiments.
Yeah.
First of all, and the setup here was sounds like it was basically a capacitor setup. Was there a dielectric in the middle?
Yes, there was a dielectric of polyethylene, I think.
Polyethylene.
Yeah.
Okay. Was there a reason that you chose that, or?
Becker and Bat chose it to encourage field emission of the capacitor. So they point out in their paper, it's quite important that you get a field emission. So they took sandpaper and they roughened the capacitor plates, for example, to encourage field emission.
Interesting. Okay, and did it work with an air gap, or did the dielectric in there need to be in there?
No, the dielectric. Well, I'm not an expert on capacitor, I should say, but I think if you have an air gap, you get ionic discharge, which is not what you want. You want field emission instead.
Okay. And can you go to the to the next slide where you had the plate behind the device. I think it was one more slide further where you had.
Oh yeah, this one.
Yeah, that one where. So I'm trying to understand what's going on there. So without this plate, so they were like holding a plate behind the device, and something would happen, and they took the plate away, and something else happened.
Yes, they saw two different effects. What happened was that when they thickened the cathode, like I've shown here, the force reduced. When they put a plate disconnected from the cathode into the space, the force reduced much more and reversed.
Oh, okay, so the plate was connected to the cathode. It was in the circuit.
Yes, it was electrically part of the cathode.
So the plate that you showed behind this box in one of the versions of this slide, that plate is actually in the circuit touching the cathode.
No, that's not touching the cathode.
Okay. So so there's a metal plate behind here right now, and so is this causing anything bad or good to happen in this configuration?
You mean in the schematic?
In this schematic, when the plate is there, what is happening with the experiment? Is the experiment running at full?
The experiment is now behaving as if that plate was not there at all, because it's behind the Rindler horizon that the electrons see. So from their point of view, that plate does not exist.
Okay, now you're saying that if you take a wire and you connect that plate to the cathode and leave that plate in the same spot, something else would happen then?
I don't know what would happen. So it should also have a null effect. So it shouldn't have an effect at all on the electrons, even if it was connected to the cathode, because it's behind the Rindler horizon. So you have to assume it doesn't exist from the point of view of the electron.
And how far back is that horizon? Is it like an inch, or is it like 10 feet?
It was about 2 centimeters. Calculated 2 centimeters.
Okay. Yeah, I'm going to need to read this paper, because I don't know a lot about how these horizons work. But do you have any ideas why this one experiment was so much more powerful than the other ones? Was it?
Yes.
Is there any ideas so far?
Yeah, it follows from the theory, because the thrust is expected to increase as you increase the acceleration of the core, if you like, the material you're accelerating, and also it increases as you reduce the size of the cavity that it's confined in. And I mean, I'm not an electrical engineer, so I would not have guessed a capacitor would be the best way to do it. But Becker and Bach were engineers, electrical engineers, and this occurred to them, obviously. So the gap here is about 10 micron, and the acceleration of electrons is about 10 to the 19 meters per second, which is absolutely huge and far higher than the accelerations I was able to get in my light-based experiments.
Okay. And this is probably easy to build. Has this device been tested any other time than this one time?
This has been done several times actually over the past few decades. A similar test was done by, I think his name is Takahashi Musha, a Japanese person who did basically the same thing in 2008, maybe. I think it was 2008. And it's been done by NASA, Canning, 2003, and other times as well.
Because this will lift off the ground clearly. I mean, this can lift at least 10 kilograms off the ground, right?
Yes. Well, if we can confirm it, it means we can launch with this. So it's a very important thing to look into.
But I'm just wondering, did they flip it upward and turn it on and see if it jumped off the table? That's what I would have done. But I guess they didn't do that. But no, all right, well, I'll look at the paper. Thank you very much.
Yeah.
Thanks, Eric. Oops. Okay. And let me see. And actually, I think that probably answers several questions. I had several people asking about, Wayne was asking if the yellow block is a metal electrode, but I think a couple other folks were also asking about an experiment they could build. It sounds like this, Mike, it sounds like this block, this experiment that you have right here is maybe one that folks might want to attempt, or?
Yes. I guess you have to be careful with safety because it's 5,000 volts, isn't it? But
well, that would be the question then, because you've mentioned, and I should apologize for talking so much, but you've mentioned that B-field Brown and several other effects over the last few decades. But if people were going to build one specifically to test this, the experimentum crucis, then adding the event horizon to what appears to almost be like an asymmetrical capacitor, that sounds like that would be.
It's actually a symmetrical capacitor, this one. Well, the initial experiment was. When they changed the cathode, it wasn't, but
okay, yeah, well, thank you. And the reason I ask is Jeremiah and Mark Sokol and several others in our group are actually building things. So we might have some folks who could, do some experimental validation. And
yeah, that'd be fantastic.
Oh yeah, absolutely. Okay, well, oh, and Jeremiah had it. Okay, Jeremiah, would you like to go next, sir?
Yeah, can we shoot back to that other slide with the high density polyethylene sandwich between the plates?
Well, I don't think I show it actually in detail.
Yeah, that one. Yeah, go. Your experimental test. You have the thing about. I just wanted to also understand exactly how this system was exactly configured. It looks like on the scale you had two plates that were directly in contact with that polyethylene, and I'm just trying to figure out like what exactly is different between your experiment and just simply a parallel plate capacitor. I unfortunately I missed a little bit of your presentation earlier, and I apologize for that. So I really want to grasp what you're showing here, though.
Right. Well, I'm not an electronics expert, but the dielectric, it has to be quite subtly done. So that you put a dielectric between the two capacitor plates so that you get field emission and not discharge. Field emission of electrons.
Is what we're looking here on the bottom in that diagram, is that effectively what was on top of that scale?
Yes, that's right.
And then what's the gap between those two, what looks like metal plates, the gray bars? There's a dielectric between those?
That's the dielectric, which is polyethylene.
Okay, and what's the yellow part then? That's just
this is just my attempt to represent the energy in the Unruh wave field.
Oh, okay, thank you so much. That really helps. And what's the black line there? Just the end of the field?
That's the Windler horizon. So from this accelerating electron's point of view, that is the end of the cosmos.
Thank you. Yeah, that really helps. For some reason, I didn't quite catch that, so I'm sorry if you already explained it. Thanks for coming in again. And did you test with various voltages and see how that responded? What kind of results you got? How does voltage affect it?
Yeah, they did. And also Takaaki Musha, the Japanese experiment, they found that using, this is interesting because Paul Laviolette mentioned it in his talk, using pulsed DC multiplied the force by a factor of about 4.
And I'm guessing like that would make perfect sense within even the theories that we're familiar with, where in the asymmetrical emission. anytime you have a transient wave that has an asymmetry, you're going to end up with a radiated power that's not symmetrical between, you know, the positive side, the electron acceleration and the electron deceleration. So that's unsymmetrical radiation and should equal the force.
Okay. Yeah.
Wonderful.
Thank you. I appreciate it.
Thank you, Jeremiah. Okay, let me go to Max next, sir.
Hi, can you hear me?
Yes, absolutely. And could I get you to start your video, Max? That's okay.
I guess so. Sure, why not?
And what was your question, sir? Absolutely.
Two questions. I might have missed if Professor McCullough had an expression for the distance to the Rindler horizon. And the second question, there was I think it was a guy named Reda had a paper recently come out with some critiques of UI. I wondered if you'd answered that. Over.
Yes. Yeah, the distance to the Rindler horizon in the experiment was about 2 centimeters. So that's just calculated from the acceleration.
Okay. Did you have an expression for that? Yeah. Okay, so it's just, was it in the charts? I didn't see it.
Yeah, it's there actually. I've shown it on the schematic.
Right, the expression for it, I mean.
Oh, yeah, sorry. That is c squared over a. So it's the speed of light squared over the acceleration of the electrons, which is of the order of 10 to the 19 meters per second. And your other question, yes, yeah, I liked Render's paper a lot. I thought it was very useful. The factor I use in quantized inertia to model the changes in UNRU radiation has always been an approximation, and Render tried to calculate the full expression, and he found it was rather difficult to do.
Wonderful. Okay, well, thank you very much.
Okay.
Let me see. Does anyone else have any questions? Michael, Michael Himes, did you have a question, sir?
Yes, with regard to the dielectric and the capacitor, you say it was polyethylene. Is that a chiral molecule? What I'm hinting at here is, how does chiral spin figure in the field dynamics of your setup there?
Well, it shouldn't have much of an effect. We're only measuring the force in one direction, so.
Yeah, but the chiral spin can be engineered one way or the other, whether it's right-hand spin or left-hand spin, or a balance of the spins up and down.
Okay, well, I can make a note of it.
Okay.
What I'm building is an asymmetric resonator that is dependent upon the chiral dielectric material between a series of plates.
Are you going to try and measure thrust from that?
I know it has thrust. The US government is building it, and so is China. I had reference to the EM drive. China got a bunch of their physics clues from Schauer.
Okay.
Right.
Yeah. Well, and Michael, when we go into open discussion, if you're still with us, I would love for you to talk more about that in open discussion in a bit. Let me mute you back out for right now, and we'll see where we're at with questions. I think that Michael Boyd had one more question, and then
Hello, Mike. Could you go to the prior slide? To this one. No, one more. I passed. It was the one where you had outside the horizon slide. Not this one. I don't know. You showed it earlier. It was
this one.
This one. There you go. Okay, so now I'm trying to understand this. So the orange region, that's 2 centimeters, correct?
Yeah. Yeah.
And that dark black line is the Rindler horizon.
Yeah, that's right.
Which is about 2 centimeters away. And then the 2 parallel plates are have a 5 kV DC pulse. I mean DC applied to it, right?
Yes, that's right. Yeah.
And then that the gap is filled with what did you say the dielectric?
Polyethylene.
Polyethylene. And do you know did the dielectric have a certain polarity? Do you know?
No, I don't know.
Michael, if I could jump in really quick, one of the things that Mike McCullough had mentioned, I believe, was that there's a field effect emission of electrons that needs to happen across the dielectric.
Right. So what I'm trying to figure out is, do you know approximately what the velocity of the electrons was relative to the speed of light in that experiment? Because I could use that to calculate how much inertia the electrons had, for example. So
we calculated quite easily from the acceleration. I can't remember the exact value of the acceleration. It's about 10 to the 19 meters per second, and the distance across the gap varied from.
So that's
10 micron.
It's relativistic, is my point. It's
Yes.
So
Okay.
that those electrons are going towards the right. They're accelerating to the right.
Yeah, that's right. Yeah.
And then that gray region on the left, that's basically a baffle. What is it? A piece of metal?
Yes, piece of metal.
A piece of metal is put on that side, and it doesn't affect the experiment because it's outside that Rindler horizon, correct?
Yes. If it's on the right side of the Rindler horizon, it does affect the experiment. If it goes to the left side, it doesn't affect it.
Oh, okay. So now, you know how Puthoff's hypothesis, I hope, about space-time metrics. He has this thing he calls expanded space-time, and basically, I'm curious if you think that region, the gray part on the right, I mean on the left, excuse me, is in a region where space-time is expanded, so it wouldn't be visible to the observer outside that region.
I'm afraid I haven't read that paper of Puthoff. I read the High Schroeder Puthoff paper, and a few others of Puthoff.
Okay, I'll try to put a link on the chat so you can check that paper out. And thank you for your time.
Thank you again, Michael. Okay, let me see. Let's do Thomas Anderson, and then again, Mike. How are you doing on time, sir?
I'm fine to go. I'm good to go at the moment.
Okay, well, why don't we do Thomas Anderson, and then maybe he'll be, if it's okay, unless you'd like to stay and do more questions. I have a couple more, but let's do Thomas Anderson then. And sir.
I was just going to say on the capacitive plate, I'd like to make a suggestion. rather than a question for those
Yes,
who
sure,
might be
please.
attempting to replicate this,
Yeah, please do.
or future attempts at rebuilding this too. Have you looked into triboelectric effect?
Triboelectric.
Right, because polyethylene has an extremely strong negative triboelectric effect, right, where it readily builds up a negative charge on its surface. But if you were to layer that with like another dielectric sandwich together, like say polyurethane, which has a propensity to build up a positive charge, so that you can kind of like cut down on the amount of power necessary to generate your positive and negative charge on your plates, to see if that might have any effect, because it also might help retain the effect, since you're saying that you're wanting to try to avoid a discharge effect where the energy is being, I'm assuming you mean by discharge, you mean like a coronal effect?
Yes, I think they try to avoid that.
Right.
So
So that,
use different dielectrics to cancel each other out in terms of charge.
right. That might, I'm just thinking that might help, and it might help kind of shortcut the need for the nanomaterials to at least get a good start on like establishing the technology, so that the nanomaterials would then, follow afterwards, because it'd be like, well, if we can improve this to make this even better, why not invest the energy and the time, just like we invested so much energy and time in electric motors that we've gone from a little spinning wire on a mercury pool to driving electric cars now. So
Yeah, okay, thanks. That's a good suggestion. I'll make a note of that as well.
thanks for hearing. So
Thanks.
Okay, let's go to Jeremy Reese next. And thank you, Thomas.
Hey, Mike, I had a question from our live chat from, what was his name? Oh, sorry. He wants to know, when I find his name, he wants to know if you can talk more about general relativity and how your theory fits in with Einstein. Because our last speaker threw Einstein in the trash, and we want to know, do you keep GR, right? And your theory is in accordance with GR, right?
Yes, it is in the solar system. So what it looks like is, okay, so Einstein in 1911, he came up with an early version of general relativity called the variable speed of light version of general relativity, but he made a factor of 2 error. So he got rid of this theory and went on to a geometrical one using a space-time metric. Much later, Robert Dicker in 1957 rediscovered this theory and corrected the factor of 2 mistake, and found that this theory actually predicts everything that general relativity does in the solar system. So the bending of light by the sun, the delay of light in reflection from Venus, and tests like that. So this is called variable speed of light general relativity. And this past week, I've shown that I can derive this from quantized inertia. And it's exact in the solar system. But the great thing is that, unlike general relativity, which cannot predict galaxy rotation, this new version of general relativity can also predict the galaxy rotation, as well as as things like the bending of light by the sun. So anyway, I've just written a paper about this and I'm about to submit it.
Oh, actually, I find that intriguing. I had no idea that he published another paper. So is it okay to ask you, could you describe that in a little bit more detail? You said Einstein, a variable speed of light theory of relativity?
Yes, that's right. So he considered speed of light, so c is f times lambda. And if you assume that time slows down in a gravitational field, that reduces f, but also because distances shrink in a gravitational field, that reduces lambda. So the speed of light close to masses decreases. And this accounts for the fact that it bends around masses like the sun. And it predicts it exactly as well.
Oh, okay. Well, thank you. Yeah. I'd never even heard of that before. So,
I liked it right from the beginning because it fits more with my theory of quantized inertia, which uses a flat space, and I don't like bent space because you can't directly test it.
Yeah, absolutely. Well, does anyone else have any more questions?
That question was from Greg Chase, and he says, "Thank you, Michael. He let's hope it gets published."
Jeremy, do you have any more YouTube questions?
One more question from YouTube I have one from Gardy Pierce. He wants to know, is there an implosive technology physics division degree? I'm not sure what that means.
Did you refer to Schauberger, who had an implosive device?
Yeah, I think that's what he means. And then I think he had another question about what are correlations with cavity structural effects, quaternion spinners, and Hopf fibrations?
Oh, well, I don't know. I don't know about that last one.
I know about Hopf algebras. I'm going to have to look that other Hopf fibrations. I've never heard of that before. I'm going to have to look those up. And I've heard of direct spinners, but
chaos theory or something.
Because I was like, you know about Roger Penrose's twister theory, right? That he published in 60. He started that in 67, but then I guess they're saying that that's just direct spinners reinterpreted or something. I don't know. But interesting stuff.
Yeah, that doesn't seem to be testable to me.
You get lost in a lot of math, yeah.
Yeah.
But we're building stuff and we're going to test it, and this is awesome, and I hope you get that published. One question from Peter Middleton: is the gray metal plate charged on the far left and plus or minus? And if so, with what voltage? So the gray metal plate on the left, so that one that's beyond the Rindler horizon, that plate, is that charged, or what are you doing with that plate? Is that grounded? Is it just, what do you do with that plate? And then
I'm afraid I don't know. It's all in the paper. I think it's probably grounded, but I'm not sure. I better not speak if I'm not sure about it.
Excellent. All right.
Wonderful. What, Jeremy, was that everything from YouTube,
or is it just neutral? Yeah, that's what he was asking. But yeah, I'm not sure. You could probably do a lot of different things with it, and it might be different for different sides of the craft, depending on what side of the craft that's on. Because I assume that if you make the whole craft out of that material, then it's going to be different on different sides to get an asymmetric effect across the craft.
I know there's been a lot of excitement about Mike's theory. There has been a lot of excitement. I've gotten several, probably 5 or 6 emails that immediately come to mind from people who were like, wow, we're really excited that he's coming on to speak. So I would love for some of the folks who are excited to test this, to build tests and hopefully support his model, and then hopefully find things that maybe could elaborate on, right, to refine the theory or come up with next steps for it.
That would be a real help.
Yeah.
I mean, people like Frank Becker coming in with an experiment was a great help.
Yeah, well, and hopefully Mark and Jeremiah, in fact, Jeremiah is on next, so hopefully Jeremiah will promise to do an experimental test on this. And they do really good work, and they do good measurements. So
thank you, Mike.
Thanks.
Yeah,
So let me see, and it's 3:41 now. Are we all set, guys, for questions? I think Jonathan Lane had one more. Why don't we finish up with Jonathan Lane? We'll be at a few minutes ahead of schedule for. Go ahead, sir.
Okay, so one question about the comparisons with general relativity. You'd mentioned in, I believe it was on Twitter, that wormholes would not exist because space would be flat, but that it would be possible to create a horizon effect that would allow you to jump over space. How would that work?
Yeah, so I'm a very strong follower of Mach. And his kind of idea was that if you can't in principle measure something, then it doesn't exist.
Mhm.
And this is why I like horizons very much. It's like the slide we're looking at now. That plate on the left does not exist from the point of view of the electrons that are accelerating so rapidly. The Rindler horizon has effectively chopped off part of space for them. So, I mean, I don't know exactly how to do it, but if you could arrange horizons to chop off part of space, then you could simply step over it.
Okay.
That's the idea.
Okay. So thank you, Jonathan. So I think with that, or actually, you know what? Let me, if it's okay, Mark had a question, and Wayne actually had a question as well. Mark, would you like to go, sir?
Oh yeah, thank you very much, Mike, for putting this presentation together. I missed a little part of it, but the part about the parallel plate capacitor, or the asymmetric parallel plate capacitor, is that just a asymmetric parallel plate capacitor charged up, or is there anything else that we'd have to add? Because this is something that I've already tried in many variations.
Yeah.
I believe it's symmetrical, Mark, and that's my apologies. I said asymmetric, but he said symmetrical.
It's symmetrical, and you need a dielectric between the plates to encourage field emission, and you don't want to have discharges, ionic discharges. You want field emission of electrons instead.
So a high K dielectric like CCTO or barium titanate?
I don't know. They use polyethylene, so something like that.
That's a high strength dielectric polyethylene that would withstand, but it doesn't have a high K factor. It doesn't like accept a lot of charge.
Mark, do you think that you guys could build something like this as a test?
Yeah, I can actually chime in here too. As far as why to use polyethylene, take for example some of the test data done on polyethylene and Teflon. Teflon would in fact be possibly even better, because those dielectrics, although they don't have a very high K, they have an incredibly fast RF response, which is why they're oftentimes used in the jackets of RF cables. Because they can basically take those kinds of transients. So it would really be ideal if you're trying to create a wave front from one side to the other that's effectively fast and has a very sharp transient, then those materials are not going to eat that transient up.
Oh, so this is a pulsed parallel plate capacitor, right?
Yeah, that is a good question. Would you mind, Mike, answering how these capacitors are driven? What kind of waveforms are input into these devices?
Oh, it's just at the moment it's constant, but the experiment I described by T. Musher, he used pulsed DC, which he found increased the effect by four times.
Do you have any idea as far as what kind of frequency he was pulsing at, or what kind of rise times he had?
Do I have the paper here?
Oh, you do? Well, that's convenient.
Yeah.
Yeah, we're wondering about the symmetry of the waveform, whether it was a sinusoidal or an impulse type waveform.
Yeah, let me just stop screen sharing for a minute.
I did see something in the slide deck that made it look like it was kind of a pulsed sawtooth wave, which reminds me of the flyback stuff that we are all very familiar with.
Yeah, sorry, I can't find my copy of it. So, but if you could email me, I'll try and send a scanned copy to you.
Thanks, we appreciate it. That sounds good. No problem.
Yeah. Sorry about that.
Thanks again, Mike. Well, let's do this. Why don't we? I think that we're all pretty much set for questions.
You're here about the motor?
I am.
Oh, sorry about that. Okay. I think that we're all pretty much set for questions. So why don't we?
Eric Herman sent a question.
Oh, okay, Eric. Why don't you go real quick, and then we'll call it a day with that for the questions.
Okay, Mike. So I don't understand horizons well, and so this might not be a valid question, and we can talk about it next week. But you know, I'm thinking about this, and as a particle moves and things vanish behind it, correct?
Yes,
The
behind the
information
Yeah.
behind it. And so, you know that I'm not a fan of the quantum vacuum, because there are celestial photon studies, transit studies, that show that there's no fluctuations happening that cause the photons to arrive with dispersion or anything like that. But let's assume that there are fluctuations. These fluctuations must be keeping particles stable, particles that can decay. If the vacuum's at play, then they're probably contributing to the stability of radioactive particles. And so if you have something that can decay, that's moving or accelerating, and you cut the legs off.
Yeah.
I mean, well, so in other words, won't decay rates start changing if this was really happening?
Yeah, that's the prediction. That's a good point you make. It is a prediction of this. Yeah.
It really. Okay.
Yeah, I hadn't considered that before, but yes, you're correct.
Like, would it be a huge, or like a minuscule change that would be very, very hard to detect, or would it be something that people really haven't looked at much yet?
I would expect it to be fairly small, depending on the acceleration you impose. I mean, I guess if you had a particle moving around the collider at CERN with a very high acceleration, it might become observable.
Okay, so we're talking about collider level energies, not not these experiments here. We're talking about CERN type stuff. Okay. All right, that was it. Thank you.
Thank you again, Eric. Okay, well, let me see. Why don't we? Why don't I mute everyone? Okay. And I will go to gallery view. And everyone, let's do a giant thank you again for Mike. Mike, thank you very, very, very much. That was an amazing presentation. That was truly remarkable.